Welcome back to ECE 501B. Homework number 8 is due on Wednesday. You can turn that into my mailbox. You can turn it in to the Dropbox on D2L, or you can bring it to class on Wednesday. We've answered the in-class lecture question that was being raised. I think the answer was yes. It wasn't a resounding yes, but there were enough votes that said they would like to be in class. So now I'll have an audience, and we'll see what we'll be talking about, whether that will be Chapter 7, Chapter 8, Chapter 9, or Chapter 10. We're going to try to go through those rather quickly. But today, and just as a reminder, our final exam is that's not right. It's not on a Wednesday, is it? It's a Monday. I've been harping on when that is, and then I write it down wrong, but it's Monday the 16th of December from 6 p.m. to 8 p.m. Make sure that's correct. But I'll keep reminding us of when that is, that final exam. But it is later. It is 6 to 8 on Monday the 16th of December. And that's not too far away. It's about 3 weeks away, I believe. So next Monday is the 1st of December, and then it's 2 weeks. Why does that date? Oh, no. Sunday is on the 1st. So next Monday is the 2nd, isn't it? So next Monday is the 2nd, and 14 days from that should be the 16th. Well, we'll see how lecture goes today. But today what we want to do is get through most of Chapter 7, if not finish it up. And the last theorem in Chapter 7 is Theorem 46. And that's on the singular value decomposition. Before we get there, we will just remind ourselves of where we stopped last time, which was this idea that we can decompose any operator into two pieces or two factors. One factor that essentially does a scaling associated with that mapping or that operator, and we form this positive operator, which is the positive square root of t adjoint t, and then we can direct that operator with an isometry. And that's this direction mapping S. We will prove that polar decomposition rather quickly maybe, but it's kind of a jumping back and forth proof, so you kind of eventually at the end you put all the pieces together, you can convince yourself that yes, we can separate a operator into two pieces, a scaling piece and a direction piece. Then we will talk about what these eigenvalues of this positive square root of t adjoint t represent. We will call those singular values of this operator t, and those are your scaling values. The book gives us an example dealing with singular values and a linear operator t. We'll then state the singular value decomposition and discuss it a little bit and hopefully give an example of the singular value decomposition. Really what that does is given any map, not just an operator, but given any linear map with the singular value decomposition, you can now identify the four fundamental subspaces. Let's look at it from a matrix perspective. If somebody gives you a matrix, and it's not necessarily a square matrix, so it's just a linear map, then the singular value decomposition can find a basis for the range space. Let's call that map linear map A. We can find the range space of A or a basis for that. We can find the perpendicular of that range space, a basis for that. We can also find the null space of that matrix A, and we can find an orthogonal complement to that range space, or that null space. So there are 4 fundamental subspaces of a matrix, and they all come as a result of this singular value decomposition. And we'll work through an example of that. I think an example might be more insightful or more helpful than just talking about it in general. Here's where we were last time. We were talking about this solar decomposition, a polar decomposition, which was theorem 741 in chapter 7. If we're given a linear operator T on this inner product space V, then there actually can be found an isometry S that's also a linear operator on that same inner product space V, such that this linear operator T can be decomposed into an isometry times this positive operator, where the positive operator is actually the square root of the product of the adjoint of T with T. That's the polar decomposition. Now let's see if we can put together a justification or a proof of that particular theorem. So here is our proof that any linear operator T can be decomposed into 2 parts, an isometry part times this positive operator part. First thing that we want to do is really just see that that square root, positive square root of T adjoint T scales the same way that T does. Because the isometry doesn't do any scaling, it just does direction. So first, let's just say that we'll take a linear operator T that's associated with this inner product space V. Then let's look at the norm squared of TV. And in an inner product space, we know that the norm squared is simply the inner product of TV with itself. That's the definition of the square of the norm in an inner product space. Now, what we're going to do is we're just going to rewrite that second slot TV as an adjoint of an adjoint. We know T can be written as T adjoint adjoint, meaning this can be rewritten as TV, and it can also be stated as the adjoint of T adjoint V. That's an equality. But now what we want to do is realize that use the definition of the adjoint. The definition of the adjoint says, oh, if you had some operator adjointed, that's the same as, or that's the definition of the adjoint, as moving that operator in front of the first slot. And if we take the adjoint of the adjoint of the adjoint, we're just left with the adjoint appearing prior to that vector in the first slot. Meaning, what I really wanted to do was say that inner product of TV is now the inner product of T adjoint with TV and V. Is that okay? So that's really just using the definition of the adjoint, that step. Now what I want to do is Now that I have this operator, T adjoint T, I know that that's a positive operator. And anytime I have a positive operator, I can actually split that or find its positive square root and form the product of that positive square root with itself to obtain T adjoint T. So that now I'm going to just rewrite that T adjoint T as the positive square root of T adjoint T with itself. That's just basically using the fact or some of these theorems that we've been using all along or introduced. We have theorem 727, which talks about a positive operator, and then I think it's proposition 728 that allows us to find this positive square root of a positive operator. We've simply split or rewritten T adjoint T as a product of two square roots of that same operator, T adjoint T. Now we're going to do the magic that we just had before with respect to the definition of the adjoint, which means now let's take this first positive square root, take its adjoint and put it over in the second slot, but that square root of T adjoint T is self-adjoint, so we don't really need to worry about forming its adjoint. We can now say that this inner product is now the square root of T adjoint T, V, with the square root of T adjoint T, V. Again, this is just from the definition of the adjoint. But now, what can we say about that inner product? We have the same vector in both slots, so now we can say that that's the same as the norm squared of the positive square root of T adjoint T. And now we've shown that this norm squared of TV is the same, or it's equal to, the square of the norm of the square root of T adjoint T, V. Meaning, we've now shown that, and I can take the square root of both sides so I can remove that square. We've now shown that the norm of TV is the same or equal to the norm of the positive square root of T adjoint T for all V. Which really means that this positive square root of T adjoint T has the same effect in a norm sense or scaling sense as T does. So now this square root, positive square root of T adjoint T has the same effect on norms as T. And that's a good thing because we know the isometry, that S, isn't going to be scaling anything. And we are just saying in this polar decomposition that we want to separate or factor any operator T into a direction term, this S operator, and this square root of T adjoint T. And what we just have demonstrated is that the norm of the square root of T adjoint T is the same as the norm of T for all vectors V when we look at TV and the square root of T adjoint T with V. So this positive square root of T adjoint T is the same in a norm sense as T is. And that's good since this matrix S, which was an isometry, cannot adjust the norm by definition of that isometry. Therefore, this square root of T adjoint T in this polar factorization or polar decomposition is going to work the way it's supposed to. Now we need to figure out, is there an isometry that will do the other piece of this operation of T? But is there such an S matrix? And let's just sort of state the idea of what we're going to try to show next. The idea is we are actually going to create a piece of S, which we're going to call S sub 1, and that operator is going to take the range space of this positive square root of T dagger T into the range space of T itself. And that may not fill up the whole space, so we need to then extend this map S sub 1, or this operator S sub 1, to form or to create an isometry, or to basically complete the entire space to form S. So S we're going to sort of break into two pieces. One piece will map the range space of this positive square root of T dagger T onto the range space of T. Then we will look at the orthogonal complement, or the perp, of the range space of the positive square root of T dagger T, and get another mapping on it to the orthogonal complement of the range space of T. Then we have this decomposition that we need, and now we can create S out of those two pieces with S1 and S2. So let's first define a map for S sub 1. So the first thing we want to do is define a map that takes the range of this positive square root of T dagger T into the range space of T. Meaning here is S1, and we want that to take all of these vectors into TV. Meaning this is now the input to S1, and this you could think of as the output. And the hope is we can extend S1 to an isometry meeting our needs for S. So we're wanting an isometry S, and the range space of T may not be filling up the entire space of the dimension of the domain of T. So now let's build this piece up. We're really wanting S, an isometry that operates on T dagger T. We want that to equal T. And that really means that for all vectors V, S square root of T dagger TV should be the same as TV. In our, let's say, complex inner product space V. Now S1 has actually been chosen to make that true. S1 has been chosen That's how we defined S1. We defined a map S1 such that if we gave S1 a vector, then that would produce T times V, where the vector that we were giving S1 was that vector V operated on by the positive square root of T dagger T. So that's how we're defining S1. So S1 has been chosen to make this true. Now what we need to do is make sure that S1 really makes sense. Is it well behaved? Is it basically well defined? Is it a well defined linear map? Let's now just state that. But does this make this map S1 well defined? And to check it whether it's well defined or not, we're going to make sure that S1 is a unique map, or it produces a unique map, and that it is a linear map. So the first thing, let's check the uniqueness of the map S1. Or to do that, we're going to offer up a statement and then see if we can actually prove that statement of uniqueness. Here's our statement. If the positive square root of T dagger T V1 is equal to the positive square root of T dagger T V2, then if that's true, if we take a V1 and a V2 and operate on those with the same operator, positive square root of T dagger T, then we better get that T V1 must equal T V2. need to make sure that we're getting to the same place from V1 and V2 if we go through these positive square roots, because what we're doing is we are saying up here that if we had a V1 here and a V1 here, and they took us to two different places, then S1 isn't going to make any sense. So we need to make sure that we're working with unique vectors. And if V1 and V2 are such that this equality is true, then we need to make sure that TV1 is equal to TV2. So let's now try to prove that. So now we have proofs within proofs within proofs, don't we? So here is now a proof of this last piece. We have TV1 minus TV2, and we're really trying to drive that to 0, or to show that that's equal to 0 if the positive square root of T dagger T operating on V1 and V2 is equal to 0, or is equal. So here's what we have. We can use the linearity of the linear map T to give us that. That's valid. But then what did we just show above for T and T dagger? Way up here, didn't we show that those were equal in norm? In this most recent proof that we're working on, we have TV. Now we're going to use this result that we just validated or showed for T and the square root of T dagger T. So that now if we have the norm of T, quantity V1 minus V2, we know that that's the same as T dagger T, V1 minus V2. That we did above. But now we can just do the linearity again. We can say, well, that's now equal to the norm of the positive square root of T dagger T V1 minus the positive square root of T dagger T V2. But in our statement, if T dagger positive square root of T dagger T V1 is equal to the positive square root of T dagger T V2, then we know this last line is equal to 0. So if the premise of our statement, or if the hypothesis of our first statement is true, then this is 0, and now we've just concluded that that norm is 0. So that now we do have that from linearity, I guess that was this one. And from the statement, or from the hypothesis of our statement, then we are guaranteed that that's 0. So now we have this uniqueness property true, or validated, for this positive square root of T dagger T and T. Now what we want to do is check the linearity of the map. Again, we're playing with S1 and trying to make sure that it's a valid linear map. So now we've shown that uniqueness properties hold. Now we want to check the linearity of the map. And we can do that in the two pieces. We can check homogeneity and the addition property. Homogeneity says, okay, if we have S1 operating on this positive square root of T dagger T V, homogeneity, we want to look at a scaled version of a vector V. But what do we know about this from just the definition of S1? It needs to be equal to T times AV, right? By the definition of A1 or S1. So this is now true by our definition of S1. But now T is a linear map or a linear operator. So this is now A, T, V by the linearity property of T. But now use the definition of S1 again on TV, and now we have A, S1 of this positive square root of T dagger T, V. And that's now showing homogeneity of S1. So that's sort of an inter proof. Now let's look at the additivity or the addition property of this map S1. If we have S1 operating on T dagger T, V1 plus V2, then again we can use the definition of S1 to say, well, that's the same as T operating on V1 plus V2 by definition of S1. But now we have TV1 plus TV2. And again, we can use the definition of S1 in the other way. We now say S1 is this operating on the positive square root of T dagger TV1 plus S1 positive square root of T dagger TV2. And that's now showing the addition property of S1. So now our map S1 is well behaved. It's unique or has this uniqueness property, and it is a linear map. Now what we want to do, and now we can go back to some of these earlier results from a couple of equations, 742 and 743, we can actually claim that S1U, that norm, is equal to the norm of U. As long as all of these U's, let's say for all vectors U, living in the range of this positive square root of T dagger T, or positive square root of T dagger T. Meaning, let me just sort of remind ourselves of 742 and 743. 742 was the fact that this norm of TV is equal to the norm of the positive square root of T dagger T V. That we showed. 743 said that we had S1 positive square root of T dagger T, let me say V again, is equal to T V. So now if we just sort of work from this side and go back through this, let's now take the norm of TV. If we take the norm of TV, then from 743, that's equal to the norm of S1 positive square root of T dagger T V. But we know because S is an or by the definition or by 742, this is now the norm of, we have TV is equal to this. So now we can put that over here, and we've sort of squeezed this in between the two. So we've shown that TV is equal to the positive square root of T dagger TV. We're going to put that over here. And we can say, since TV is equal to S1 square root of positive square root of T dagger TV, we can equate their norms. So now we have that second piece that we wanted, which is really to say that if we view this as some vector u, then we have the norm of S1u is equal to the norm of u for all u in the range of this positive square root of T dagger T. And that's what we have here for our u. U is now in the range of positive square root of T dagger T, and u is in the range of, and it's the same. So we have S1u's norm is equal to the norm of u. So that's the aside for where this particular statement is coming from, that we have the norm of S1u equal to u for all u in the range of the positive square root of T dagger T. Now, if we know that, if these are equal in norm, then the only way that S1u can equal 0 is if u is equal to 0, meaning we can't have S1 having a non-trivial null space. Otherwise, we would have a bigger norm of u than S1u might be in norm if S1 had a non-trivial null space. So that now that S1 has a trivial null space, we now know that S1 is injective. And now we can play all of those games that we know about maps being injective. So we know S1 is injective from this norm relationship. And that's true on what? U was a member of the range of this positive square root of T dagger T. So that now, since we know that it's injective, we can see that the dimensions are going to be the same between the range space of T dagger, positive square root of T dagger T's range, and the range of T. So the dimension of the range of T dagger T is equal to the dimension of the range of T. And because those two are equal, now we can equate the dimension of their orthogonal complements. We now know that the dimension of the range, of the orthogonal complement of the positive square root of T dagger T is equal to the dimension of the range of the orthogonal complement of T. If we now have these two spaces with the same dimension, we can find an orthonormal basis for the one on the left, and we can find an orthonormal basis for the one on the right of these in this last line. So now we can find we now have orthonormal bases for the range of positive square root of t dagger t perp and the orthogonal complement of the range of t have the same length or have the same number of basis vectors. So these orthonormal bases on those two spaces are the same length or have the same number of vectors. If that's the case, let's just select some. So now let's choose E1 E sub m to be our orthonormal basis on the range of t dagger t perp. And let's say F1 through F sub m on the range of t perp. So now we have two orthonormal bases on two different spaces. And now what we want to do is we want to basically be able to map one to the other or find a mapping from these E's to the F's. And we can do that with an isometry. So now we can define another map. We're trying to extend S1. S1 was mapping between the range of the two spaces. Now we want to find a way of connecting these orthogonal complements to those two original spaces. So we're going to now define another map. And we'll call that S2, such that A1E1 plus dot 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 plus, let's say, A sub m EM is equal to the same scaling factor, A1F1 plus A sub m F sub m. And this map is actually going from the range of the positive square root of t dagger t perp into the range of t perp. And it's critical that we're actually keeping the same weighting coefficients between the two. A1 through AM are the same in both expansions for S2 and A1. I'm sorry, for E's and F's. So that now we have the isometry that we wanted. We can combine S1 and S2. S1 was working on the range of those spaces. S2 is working on their orthogonal complements. And that allows us then to have this direct sum decomposition of our underlying vector space. So now define S. Let me just call it an operator. S. S is going to be S1 on the range of positive square root of t dagger t, and it's going to be S2 on the orthogonal complement to that. Or the perp. And because this separation of the space of this of the domain space, something in here is orthogonal to, by definition, its perpendicular, or its orthogonal complement. So now we have this direct sum decomposition of the original underlying space, V. Because there is a direct sum relationship between these two spaces, between the range of t dagger t and its orthogonal complement, we can then take any vector little v in our vector space V and represent it into two different pieces. Any vector V can be uniquely, that's the nice part about the direct sum decomposition, as V is equal to U plus W, with U belonging to the range space of the positive square root of t dagger t, and W in the orthogonal complement to that. If that's the case, now if I look at SV, I can write that, I can separate V into two pieces. U, that's in the range of the positive square root of t dagger t, and W, which is in the orthogonal complement to V, or to U. So now we have S1U plus S2W. And what we want to do is look at this map, S in total, S positive square root of t dagger t. Now consider S square root of t dagger t V. So now we have S operating on positive square root of t dagger t V. As a vector, where does this positive square root of t dagger t V live? It's in the range of that operator, isn't it? Which is the positive square root of t dagger t. Well, if that's the case, then based on how S decomposes into S1 and S2, then S when operating on a vector in the range space of square root of positive square root of t dagger t, it's just going to be S1, that vector, because everything else is going to disappear or is orthogonal to that. So as long as that vector is in the range space of this positive square root of t dagger t, then we can rewrite that equivalently as S1, positive square root of t dagger t v. But that's what we defined S1 to be. We defined that to be t v. So now this S, positive square root of t dagger tv, is equal to tv, and that's what we wanted in our original statement. So this decomposition works. For all vectors v in our original vector space, capital V. And now what we need to show is, or try to determine, if that S is indeed an isometry. So now what do we need to show that must equal? If it's an isometry, then that better be equal to V normed squared. So that's what we're hoping to show with all of these pieces that we've now tried to build up. But this now is equal to SU plus SW squared. Whoops. And if I break V into its two pieces, U and W, then I only have to worry about S1 operating on U and S2 operating on W. That's how we've defined or built up S. But now, if I have the norm squared, what's that equal to in terms of inner product? S1U plus S2W with itself, isn't it? And now if I push or create all four of those combinations of products, I now have the inner product of S1U with itself. I could take the last one, S2W with itself, and now I could look at all those cross pieces. I have S1U with S2W, and I have S2W with S1U. Can I simplify those four inner products in any way? What do I know about U and W and when they're operated on by S1 and S2? This was in the range space, and this was in the perp of that, wasn't it? And likewise for W and U. So those are going to vanish. Those are orthogonal. These two inner product terms disappear. And now I'm just left with those top two, but those top two look just like norm squareds, don't they? I now have the norm of S1U squared plus the norm of S2W squared. But S1 and S2 were isometries by the way we constructed those. So now, what if I brought this this piece down, I now have SV squared is equal to that. But S1 and S2 by construction were our isometries. Which now allows me to say that this norm of SV squared, if S1U is an isometry, now that's equal to U squared. Well, let me go ahead and show it all. This is now S1U squared plus S2W squared. But this is now just U squared plus W squared. But since U and W were orthogonal to each other, or orthogonal complements of each other, that's now just the Pythagorean theorem generalized. This is now V squared. And that's what we set out to show. To show that S was an isometry, we needed the norm of SV to equal the norm of V. We could take the square root of both sides to show that. So now S is in fact an isometry, and we now have basically gone all the way around and shown that we do have this polar decomposition. Any linear operator T can be split into two pieces, or two factors, an isometry factor and this positive square root factor. One scales and the other one rotates. So now let's just sort of discuss a little bit about what that provides us or gives us. So any linear operator, that was T, can be decomposed as a product of an isometry and a positive operator. And we can go back in chapter 7 and remind ourselves of what these two pieces give us or provide us with in terms of the isometry and the positive operator. We can now understand how these operator classes or classes of operators work. So we can now apply, that understanding to gain knowledge of any general operator. Now what we need to keep track of is we've actually sort of introduced a curve here a little bit. We've actually sort of had a couple of different bases floating around. Note that basis, meaning we have a basis for the isometry and we have a basis for the positive operator. Note that basis, where these operators have nice representations, may not be the same. Usually when we talk about an operator, we sort of keep one basis in mind, but now we have two bases that are potentially available to us to sort of think about the isometry and the positive operator. It might be nice to think of those under two different bases. We also can also be viewed as a statement. This particular factorization, or this polar decomposition, can also be viewed as a statement about matrix factorization. And if you get confused, just think of the polar form of a complex number. It has a magnitude and an angle. That's basically what we've sort of done here. Here, with a matrix factorization, any matrix can be factored into two matrices. One of those matrix factors has eigenvalues with magnitude 1. One matrix factor has eigenvalues with magnitude equal to 1, and one matrix factor has not non-singular but non-negative eigenvalues. In this polar decomposition, we have the two parts. The positive operator is this positive square root of t dagger t, and we actually give the eigenvalues of that positive square root of t dagger t a name. So in the polar decomposition, the positive operator is the positive square root of t dagger t, and we actually call the eigenvalues, remember that was one of the factors in our linear operator t, so we call the eigenvalues of the positive square root of t dagger t the singular values of t. Now we know something about the positive square root of t dagger t, about their eigenvalues. since the positive square root of t dagger t is a positive operator, what do we know about the singular values of t? Or first off, what do we know about the eigenvalues of this positive operator? If I give you a positive operator, what do we know about the eigenvalues of that positive operator? Pardon? They're real and non-negative, aren't they? We don't have any negative eigenvalues for this That's one of the, maybe this is sort of mislabeled. We should say since the positive square root of t dagger t is non-negative, that's maybe a better way of stating it, but in general, or historically, they just call it positive. So now that it's positive, we know that the eigenvalues of this positive square root of t dagger t are non-negative, but those are the singular values of t. So now we know the singular values of t are non-negative. We aren't going to have any negative singular values. So all of these singular values of the matrix T are corresponding to the eigenvalues of this positive matrix, positive square root of t dagger t. So since that operator is positive, the singular values of t are always non-negative. So if somebody gives you a negative singular value, you go, wait a minute, there's a typo or something's wrong. All of the singular values of a linear operator need to be, or any map, are non-negative. They can be zero, but they're going to be non-negative. The other thing that we need to keep track of is some of those eigenvalues of the positive square root of t dagger t may be repeated. So we repeat each eigenvalue based on the size or the dimension of the null space of the positive square root of t dagger t minus lambda I. If the null space of this positive square root of t dagger t has dimension 1, then we have just one eigenvalue for that particular value. If this is bigger, if we said, oh, we have an eigenvalue of the positive square root of t dagger t that's equal to 2, and we look at the dimension of the null space of the positive square root of t dagger t minus 2i, and we see that it's 3, then we know we have actually 3 singular values at 2 for the original operator t. Let's look at an example. Get something we can sort of grab onto or chew on for a while. Maybe all of these proofs and statements are starting to make our heads spin. This is example 45 in chapter 7. And let's just see if we can find the eigenvalues of a linear map or a linear operator. Suppose that we now have a t, and it's operating on a 4-dimensional space, and these are z's, so this could be real or complex vector space that we're living on. And suppose that we take these 4 coordinates, z1, z2, z3, z4, through this linear operator t, and it produces 0, 3z1, 2z2, and minus 3z4. 4. Can you tell me what the matrix representation of that linear operator looks like? First off, how big is that matrix? It's 4 by 4, right? We're in a four-dimensional space, so this matrix needs to be 4 by 4. Can you tell me what the top row looks like? I'm taking this matrix and let's say post-multiplying by a vector z1, z2, z3, z4 and producing 0. That's what that linear map is telling me. So that now I better hit every one of those coordinates, z1, z2, z3, with a scaling factor of 0. What's the second row in this matrix representation of T look like? I'm just pulling off the top coordinate and scaling it by 3. What about the third row of this matrix representation? I'm just pulling off the second coordinate of my original vector, z1, z2, z3, z4, and scaling it by 2. So that requires a third row of 0, 2, 0, 0. What about the fourth row? Does everybody see that? That's now the matrix representation of T associated with this linear map T. Now, can you tell me the eigenvalues of that matrix representation? Are they screaming at you? What do we have as far as this matrix representation? Does it have any nice structure to it? And by that, you're first saying, is it diagonal? If it's diagonal, then I can immediately tell you what the eigenvalues are. It's not diagonal, darn. But, wait a minute, it has an awfully lot of zeros in it. It's actually triangular, lower triangular, isn't it? Anytime you have a triangular matrix, either lower triangular or upper triangular, where are your eigenvalues? They're still on the diagonal, aren't they? So how many unique eigenvalues do we have? We have a 0 eigenvalue, and we have an eigenvalue of -3. So we only really have 2 distinct eigenvalues for this particular linear operator. The eigenvalues here are 0 and -3. Now, my screen's not big enough, so you'll have to sort of remember this. Now what I want to do is get the matrix representation of the adjoint of this. This now doesn't have any complex numbers in it, so we just have to transpose it, don't we? We could do the complex conjugate transpose. If we do the complex conjugate, it's the same. We just transpose that. So now I'm going to give you the matrix representation of the adjoint of T, which really just says flip everything across the diagonal. Take the transpose of that. So that's what I'm going to write down now. I'm going to say the matrix representation of T dagger is equal to 0, 3, 0, 0, 0, 0, 2, 0, 0, 0, 0, 0, 0, 0, 0, -3. What's the linear map of this adjoint written in terms of coordinates? So the first entry is going to take 3 times the second coordinate, isn't it? The second entry is 2 times Z3. The third coordinate and the fourth coordinate. Now, if I take this and multiply it by that, I'm going to actually obtain the matrix representation of T dagger T. So now if I take T dagger, I'm going to say, oh, take this 3 times the second row of T. And that'll be my first row of T dagger T. So I now scale that second row by 3. That's going to give me a 9, 0, 0, 0. If I now look for the second row of T dagger T, that's going to be 2 times the third row. And that's now 0, 4, 0, 0. What's my third row? Nil, right? I have 0 times everything. And what's the fourth row? I now need to scale the fourth row by -3, and the fourth row was everything but -3 in the last entry. So now if I wanted T dagger T, sorry, I'm going a little bit over, but I think this is maybe going to be somewhat helpful. What does this look like? That's 9Z1, 4Z2, 0, 9Z4. Nice, those are perfect squares, aren't they? So that now if I look at this positive square root of T dagger T operating on these 4 coordinates, that would just be 3Z1, 2Z2, 0, and 3Z4. And those are all on the diagonal, aren't they? So the eigenvalues of this positive square root of T dagger T are what? 3, 2, 0. Well, if I repeat them, maybe I shouldn't repeat them. So that I now have 3, 2, and 0, right? If I take, those are all on the diagonal, so I can just take those as the eigenvalues. What are the singular values of T? Those are the eigenvalues of the positive square root of T dagger T, aren't they? So now I have 3, 3, 2, and 0. And what were the eigenvalues of T? Do you remember? To begin with, -3 and 0. So now we have a scaling of T of 3, 3, 2, and 0 associated with this linear operator. Its eigenvalues started out at -3 and 0. So we'll pick up at that point by looking at this singular value decomposition. All we've done so far now is just define what these singular values are. Now we're going to try to break that up and find basis vectors for these different subspaces associated with linear maps. And that's where we'll pick up on Wednesday.